Okay, we are at chapter 29, sources of the magnetic field. We're going to start with 29.1, the Biot-Savart Law. And let's share. Here we all recognize this as a magnetic resonance imaging machine, which has a very, very large um, magnet that produces a uniform magnetic field. Um, I used to work in nuclear magnetic resonance, so I don't know how the imaging is done, but I know about nuclear magnetic resonance. The in Orsted was the one that demonstrated um, that a current carrying wire would deflect a compass needle. It was during a demonstration in 1819. So he found that the wire deflected a nearby compass, and then in the 1820s, more connections were made by Faraday and Henry, and they showed that a moving magnet that a magnet moved near a circuit, and that a changing current, um, caused magnetism. So changing magnetic fields create an electric field, and Maxwell showed that changing electric fields uh, create magnetic fields. So in general, the source of a magnetic field is this moving electric charge. And that's what you're seeing here is Orsted's demonstration of the wire uh, causing the compass to move. So we're going to discuss the Biot-Savart law, the direction of the magnetic field. If you see here, there's a dot. We've talked about the points of an arrow. Um, so that's coming, the magnetic field is coming out of the page. The X is like the fletching on a arrow, so that's the magnetic field going in. So you can imagine this circular loop coming out of the page on the top at P and going into the page at P prime. So the dB, a portion of the magnetic field, is equal to mu zero divided by 4 pi times IDS cross R unit vector, and divided by R squared. Now, mu zero is our constant that we've seen before, the um, permeability, and E is the electric field, Ke, Q over R squared times R vector. So here is the magnetic field B is equal to mu zero I divided by 4 pi times the integral of ds cross R over R squared. So consider the magnetic, here's a quick quiz. Consider the magnetic field due to the current in the wire shown in the figure. Rank the points A, B, and C in terms of the magnitude of the magnetic field that is due to the current in just the length element ds. If you look at ds in the figure, it's just that little portion there shown from the greatest to the least. Well, B is the closest, and it's at right angles to the R. So R cross ds would be greatest there because it's at 90 degrees. And then C is a little further along, and then A is in line with S, so R cross ds would be 0. So it would be B, C, and A. So B is greater than C, is greater than A. Okay, now, so you can imagine the magnetic field around a current carrying wire using the right-hand rule. And if you point your thumb in the direction of the current, your fingers will wrap in the direction of the magnetic field. So it'll be a circle around the wire with your fingers pointing the direction of the magnetic field. So this is another right-hand rule that we're going to learn, but it's an easy one. It just shows you the direction of the magnetic field. So as a current goes through through this wire. You can imagine a bunch, just like your fingers, there's a bunch of fingers. You can imagine a bunch of little magnetic field lines going around the wire. Now, the source of the Earth's magnetic field is, there's no real magnetic particles, because the temperatures, there's such a thing as a Currei temperature, and the temperatures of the inside the Earth would be too great for any magnet to hold its polarization. So it's believed that it's the currents in the magma. Let me get the correct wording. So it's just convection currents in Earth's outer core. Charged ions or electrons circulating in the liquid outer core could produce magnetic fields just like current loop does. Now, this isn't for sure. This is just theory, and they're still trying to investigate what causes Earth's magnetism. Now, again, notice you've had this in lecture. If you've happened to miss lecture, you've missed the point that I've discussed about this. At geographic north is a south magnetic pole. It has to be. I mean, your compass, the north point of your compass is going to point to a south. You bring the south part of a magnet towards it, it'll attract it. If you point a north part of a magnet to your compass, it'll deflect it. So it has to be attracted to a south pole. So there is a magnetic south pole at the geographic north pole. It's a little confusing, but if you think about it, you'll see. And again, this donut shape of the magnetic field around the Earth is very, very idealized because of the solar wind. We've discussed that. The solar wind pushes on that magnetic field, and it even breaks it apart, breaks the magnetic field apart, and you get magnetic reconnection on the other side. That's not a topic for this chapter. It's just interesting. Okay, and we'll stop there. The next section is 29.2, magnetic force between two parallel conductors.